Okay, good morning everyone. With this last class that I'm giving, I want to prove Konsewitz's recursive formula for counting tropical plane curves satisfying point conditions for you. And we already set up quite a lot of the theory behind that, but there's still also quite something to do. Let me recall what happened at the end of last class. At the end of last class, we agreed that we wanted to fix 3D marked points for the moment. So we're working in degree D, as usual. Degree D, meaning we have D ends in the three special directions. And then we choose 3D marked ends, which at first glance look like there's one too much because we actually only need 3D minus 1 points to fix degree D curves. But then again, we don't use those to meet point conditions. So remember, we have this map pi. We convinced ourselves already that pi is a map from marked balanced fans of the same dimension. Dimension is 6D minus 1. And for that reason, we can use our old theory and deduce that the degree of pi is constant. And that is already half of the mileage, so to say. What does this map pi do? It evaluates only the x-coordinate of the first point, not both coordinates, only the y-coordinate of the second point, then evaluates the remaining points from 3 to n, and then it has a component which is a forgetful map to M04. Let's look at this picture that was also already on the board last time. The way you should think about that is, so we have h of x1, it's a point somewhere, right? But when we evaluate, we only care about the x-coordinate of this point. So we want to know, sorry, I think I should switch the points, right? The x-coordinate should be here. I only want to know where on this line this point is, right? But I don't care about the y-coordinate of this point. So it's like fixing a line condition for my point to meet. Yeah? Not a point condition, a line condition for the marked point. And analogously, the same for the second point. Now we're fixing the y-coordinate. So we ask the second point to meet that vertical line somewhere. Then we have 4 points right now. So in my example picture here, n is d is 2. Accordingly, n is 6. So we have those 2 special marked points which meet lines, and then we have 4 more points which actually meet points. And now if you look at this picture, this point sort of fixes this edge, this point fixes this edge, then this edge is also fixed, this is all fixed. But with this length you can play, right? I mean, I could sort of prolong this, and then it would still be true that the curve meets the 2 lines, because lines are, every curve meets a line because of Bézout's theorem. That's not an honest condition in a sense, right? But then on the other hand, we're also fixing the image via the forgetful map into M04 bar. And what is that? Remember the forgetful map, well, honestly, what it does is just forgets, right? And we want to forget everything but the first 4 marked ends. So 1 and 2, and 3 and 4. Yeah? So that was a picture that we also had on the board last time. So the intermediate part, sort of, connecting the 2 vertices that separate 1, 2, and 3, 4, in my picture here has length L1, L2, L3, L4. And as I vary the curve, I'm changing L1, right? So I cannot actually vary because I fixed the image of the forgetful map to be this. Yeah? So this is what actually fixes this. And what is the degree of pi now? The degree of pi, by definition, is going to be the sum over all tropical stable maps, such that pi of this tropical stable map equals this. And I want you to think of this as such that pi meets the line in one point, meets the other line in another point, meets the 4 point, and has a certain distance connecting 1, 2, and 3, 4. Yeah? That's all tropical stable maps that satisfy these conditions. And then I sum up their pi multiplicity, whatever that is. We can compute it. It's a big matrix. We can compute the determinant. At the moment, we don't know anything more about it. Okay. So this is what we've done last time, and I promised you already that the recursion would happen by sort of pulling back 2 special points in here to pick like 2 images that I like, pull them back. I know that the degree is constant, so the degree must be equal for my 2 choices. And from this equality, I'll deduce a recursion. That's the idea. To start, I have, whoopsie, I think there were better pens. To start, here's a proposition of which I give you the idea. So let me pick a point in the target space. I call it P, and P I think of as 2 lines, and then points P3 up to Pn, and an element, let me call it gamma prime in M04 bar, right? Such that the length of the bounded edge in this gamma prime element in M04 is very large. Very large. And the statement is that then every tropical stable map that maps to this P under pi will have a contracted bounded edge. Then every tropical stable map, gamma xih, with pi of gamma xih equal to P has a contracted bounded edge. Okay, what does it mean to have a contracted bounded edge? So it's going to be a bounded edge which is contracted. Adjacent are, some other edges. We're being 3-valent, of course, because we pick our points in general position. And then all the pre-images are in the interior of top-dimensional cones, meaning they are 3-valent, right? So how does the image look like locally? Let's draw a local picture of such a situation with a contracted bounded edge. This bounded edge has direction 0, so this will have some direction by balancing. This has the opposite direction, right? This will have some direction by balancing. This has the opposite direction. So in the image, it looks like 2 edges that cross somehow, but in between, there's this contracted bounded edge. And then the curves sort of go on, right? And so you can see that this contracted bounded edge, I can sort of take it, cut it open, and in that way produce something which is actually reducible. And that is the big thing, that I want to view my count of this degree of pi. I want to view the contributions to these count roughly as reducible curves, and then I count the contributions separately.
So if I wanted to be really technical, is there a way I could quantify very large?
Yes. Let me actually tell you. I write down something about the idea of proof of this proposition, and that idea of proof will also tell you something about what very large actually means. Yeah, good question. So what do? We consider all curves gamma xih that meet my 2 lines, L1 and L2, and my points, and they do not have a contracted bounded edge. And then we show that the image under the forgetful map of those curves is bounded. So here's the M04 drop, right? And you can show if you meet the lines in those points and you don't have a contracted bounded edge, then you can reach as far as here maybe, or as far as here, or I don't know, but not arbitrarily far. The set Ft of all those curves that satisfy this is bounded in M04 bar. And then very large means pick something outside, right? And so it actually depends on the choice of my two lines and my points. So it's sort of very large relative to, distances among the points and the lines. Okay. Yeah, a warning here. In this statement, we use the fact that we're working in degree D. So you can generalize. You can generalize to del pezzo surfaces, for example, P1 times P1, that's no problem. But you cannot generalize to arbitrary toric surfaces. You do need the special degree. You do need certain properties about the special degree. Okay, and then what we're going to do is we pick two point conditions with such a very long edge. We say P1 consists of two lines, L1 and L2, P3 up to Pn, and gamma 1 prime. And P2 has the same L1 and L2, P3 up to Pn, and gamma 2 prime. And gamma 1 prime, I want to be the curve that separates 1, 2, 3, and 4. And as I said, the length in between very large, okay? And gamma 2 prime, I want to be 1, 3, 2, 4. And the length in between, yet again, very large, okay? And then I know that the degree measured at P1 of pi equals the degree measured at P2 of pi. And now what we'll do is we'll analyze the curves on both sides, the tropical curves on both sides of this equation to obtain our recursive formula. That's the strategy. Okay, the first situation. So here I showed you already a sketch of what such a contracted bounded edge can be, and hopefully gave you this idea that the images then look like reducible curves and I can decompose into two components, right? But there's one other possibility. Assume we have gamma xih in pi inverse of P1. It is possible that the contracted bounded edge is actually adjacent to x1 and x2, my two marked points, right? And then the curve continues somehow. I don't really care much about how. It is possible that the curve looks like this. Then if I forget, I can just merge. Sorry, let me slow down. So let me find the blue pen for my lines. What will happen? Why can such curves exist? We fix two lines and the points P3 up to Pn, and we require our curves to go through that, right? And we know that since we are in the preimage of P1, 1 and 2 can be together, right? They are certainly, here 1 and 2 cannot be together. Yeah? They are separated by something very long. But here 1 and 2, here 1 and 2 can be together. So it's possible to have such curves in the preimage here. And now 1 is required to meet this line, and 2 is required to meet this line, right? But if they both live at the same three-valent vertex, this is all contracted, then this whole stuff here is all contracted to just one point, right? So that point has to meet both lines, but that's totally okay because it can just go here, right? So that's a legal situation. And then if I treat those two marked points as just one marked point, then it is as if I'm evaluating that marked point, both coordinates now, right? The x coordinate here and the y coordinate there, but they are the same. So I'm just evaluating a point, the x and the y coordinate for a point. So the statement is, how should I write it? Let gamma tilde, xi tilde, h tilde be the curve after, yeah, let's just say we forget x1 and let EV be the evaluation in x2 up to xn, both coordinates always now, then the multiplicity of my gamma xih of pi is equal to the multiplicity of my gamma tilde xi tilde h tilde of EV. And this is something that we are totally used to, because now we're having 3D minus 1 points. Remember, n is 3D, right? Now we're having 3D minus 1 points. We're just evaluating 3D minus 1 points here. So this is the totally usual multiplicity with which we count our rational curves through 3D minus 1 points. And yeah, so I hope that I already explained why this is happening. Nevertheless, yeah, I don't know. Do you need me to say something more about this equality of the multiplicity in terms of writing parts of the big determinant? Or do you already agree that evaluating the x coordinate of this and the y coordinate of this is as good as evaluating xy for 1 point? Do you all see that? I see many heads nodding here. Okay, so let's write down big determinants later for more complicated curves. Let's believe that. Very good. But what does it mean? What can we deduce from this lemma? It means that on the left-hand side of our equation, we'll have a contribution of nd, the number of degree d curves passing through 3D minus 1 points, right? And to make sure, on the right-hand side of the equation, we do not have something like this. Yeah, we cannot have 1 and 3 sit together and have the contracted end somewhere here. 1 and 3 in the contracted bounded edge. That would not work. Why not? Because 3 is required to meet a point and 1 is required to meet a line, and they are in general position. The point is not on the line. So this whole stuff could not be contracted to the same thing. So an analogous contribution on the right-hand side, we do not have. It only exists on the left-hand side because of the way how we picked our conditions. So now next lemma, now we consider the other curves that do not look like this, where the contracted bounded edge actually looks like this. Because if it does not only separate 1 and 2, then it has to separate something solid, so to say. You cannot just separate mark points. So let's consider another tropical stable map in the pre-image of this point configuration pi1. And of course, we assume that it counts with a non-zero multiplicity. And then what we do is we cut the contracted bounded edge to obtain two curves. Let me actually use as a shortcut, let me call this guy C, and let me call the two cut pieces C1 and C2 of degree D1 and D2, such that D1 plus D2 is D. What else do we know about C1 and C2? Well, they happen because we cut off this contracted bounded edge here, and separate those two things. And this contracted bounded edge had this very large length, which produced the image with a very large length. That means 1 and 2 must be on one side of the picture, and 3 and 4 must be on the other side of the picture. About the other points, I don't know anything at the moment. So we can say x1 and n2 are on C1, x3 and x4 on C2. Now I claim that 3d1 minus 1 further points of the remaining points meaning x5 up to xn, have to be on C1, and the remaining 3d2 minus 3 on C2 And I claim that the multiplicity of, and the pi multiplicity of my curve C before cutting is the EV multiplicity of C1 times the EV evaluation map, EV multiplicity of C2 times the intersection multiplicity at h of the contracted edge E of C1 and C2 times the intersection multiplicity at h of x1 of C1 with L1 times the intersection multiplicity at h of x2 of C1 and L2. And all those are intersection multiplicities as they appear in the Bézout theorem. And I'm slightly abusing notation here by just calling this EV. EV is supposed to be the evaluation at the 3D1 minus 1 points that I have in C1. And this EV here is supposed to be the evaluation on x3, x4, and the 3D2 minus 3 further points from here, which are on C2. Yeah? Okay, so let's prove this. Yeah, I think I want to erase this to have some space. And to prove this, essentially you just study the matrix that produces pi on C. Yeah, let's clarify a few things. We already said, okay, x1 and x2 and x3 and x4 have to be separated. They have to be on different components, so to say. What about this degree? Well, that's happening because of balancing. If I cut an edge which is just contracted, then the ends that remain on one part of the tropical curve have to be something that is balanced. And they only have the 3 directions. So there must be, for some D1, there must be D1 times this, D1 times this, D1 times this, and analogously on the other side. Yeah, so the fact that my 2 components will be curves of degree D1, D2, that is clear from that. The fact that I need exactly 3D1 minus 1 further points to live on C1 is a dimension count. If I had less points than that, in my big matrix, I would produce some 0 columns that would then yield a 0 determinant, meaning the curve does not contribute to the count. Yeah? So that this is the case is some dimension count. Well, that then is clear because these are just the remaining points. And now the one big thing that is to show is this equality of the multiplicity. And for that, we shall write down part of a big matrix. So let me yet again draw a sketch of what is happening. Here's this contracted bounded edge inside my curve C. Let's say this is minus V, this is V. This is some edge E1, some edge E2. The curve somehow continues. We don't really know how. Here's E3, here's E4, this is W, this is minus W. Now I want to go and pick a different root vertex. Until now, we have always let h of x1 be the root vertex in our, when we produce the equality from our space of stable maps to the M0 n-trop times R2, right? But we can as well claim, take another root vertex. Why is that true? If you look at your big matrix, if you pick another root vertex, what you are doing is you're just adding multiples of certain columns to another column, and that doesn't change the determinant. Yeah? So from, assume h of x1 is somewhere here also, to change from here to here, I have to, in all my columns, just subtract sort of this path from there. Okay, that works. So I can safely let this guy be the root vertex, which makes my determinant now a little bit nicer. Okay, so I will not draw the whole matrix. I will give you the relevant parts of the matrix. So I have the image of my root vertex somewhere. I'll have some length in C1. So C1 is assumed to be this part here, yeah, C1. This part here is C2. Now let me pick the length of E1, E2. I want to call those L1, L2, L3, and L4. I have then some length in C2, and I have L, the length of the contracted bounded edge. I have points which are behind E1 and which I have to evaluate. I have points behind E2. I have points behind E3, points behind E4, and I have the forgetful map. Okay. Okay, so here we'll always have our unit matrix, of course, because we're just evaluating where the root vertex goes to. Okay. Now, if I want to reach some point in E1, I might have to cross over some length in C1. I don't know. I just write a star for, I don't know, something. Yeah. Okay, I definitely have to cross over L1, and the direction vector is V, so here's a V. I do not have to cross over any of the others here. I do not have to cross over any length in C2, and I do not have to cross L. To get to a point in E2 from R, what do I have to do? Well, I don't know about the length in L1. I have to use minus V when I cross over L2. I'm not crossing over L1, not crossing over the contracted bounded edge, not crossing over anybody else here. As I go from R to somebody behind E3, now I do cross over the contracted bounded edge. However, the contracted bounded edge has direction 0, so there's still a 0. Okay, fine. I have to cross over E3, so there's a W here. There's a 0 here and a 0 here. And there's a 0 here. 0 here, something, I don't know. Okay. To reach a point in E4, I don't need to go over anybody in C1, don't need to use L1 and L2, neither L3. I need minus W here. I need something here. I do cross over the contracted bounded edge, but it has direction vector 0. Okay, and finally, what about the forgetful map? The forgetful map sums all the bounded edges which contribute to my long path between 1, 2, and 3, 4. Now, I don't know where 1, 2, and 3, 4 precisely are. 1 and 2 are somewhere here, and 3 and 4 are somewhere here. Yeah, so I might need some of those edges. I might need here. Yeah, I might also need some of those. I don't know. Might also need some of those. But what I will definitely need is this edge E. Yeah, because this is the very long edge that separates them. So this appears here. So there has to be a 1. I'm crossing once over that bounded edge. Okay, now we have a very nice and beautiful matrix, and we can learn something about it. The first thing we want to do is we want to stare at this and say, aha. So we're interested in the determinant, right? The determinant of this guy is our pi multiplicity, absolute value of determinant, okay? The absolute value of the determinant of this is this, yeah? And we want to understand why it decomposes in the way that I promised. The first thing we do is we stare at this and we say, aha, fantastic, this column is not needed to compute the determinant, and this row is also not needed. Let's erase it. We don't care about this anymore. It's gone. Okay, great. What else? Now we need to study a little bit dimensions, and I claim that this here is actually a square matrix of size 60 times 61 times 61. Okay, to see this, what do we need to do to see this? Well, we have to understand how many ends there are. This is a curve that has 3d1 degree ends, so to say. Furthermore, it has the marked ends 1 and 2. Furthermore, it has 3d1 minus 1 further marked ends, right? Yeah, so this is the number of ends. Number of ends minus 3 is the number of bounded edges, plus 2 for this column. I think I'm missing, I should sort of treat this as an end also. No, I don't have to because I can just treat this as one vertex. That should be fine. Is that actually 61 minus 1? It's just 61, huh? Yeah, okay. Oh, but I claimed it's 61. Good, okay. Good, so this is 61. So what we did now was to check that we have 61 columns, right? What about those? Yeah, well, this is because we have, so we have 2 lines for just the evaluation at x, respectively y, for 1 and 2. And then we have 2 times 3d1 minus 1 further lines for the 3d1 minus 1 further points. Okay, and that I'm pretty sure is also 61. So I think we're good. This red thing is a square matrix of size 61. Okay, yeah. Well, you know, I would sort of like to decompose that big thing into something coming from here and something coming from here. That minus v I don't like at the moment. What do? I take v times the h of r columns and add them here. Sorry, let me think first. Yeah. I take v times h of r, add them here, and then I subtract the L1 column. Yeah? Adding v times this will produce a v here and a 0 here. Subtracting this produces 0 again here and 0 here. Okay, so this is gone. Great. And here, actually, here we produced v's by adding v times the h of r columns. Yeah? Okay. Very good. Let's discuss this matrix first. This matrix has somewhere, and let me write this here, has somewhere a line. Okay, so this red guy, I give it a name, I call it A, yeah? A. And now I want to talk about A and understand more about it. A will have somewhere a line. So somewhere is x1. There are 2 adjacent edges. Let me call them L1 and L2. Not the same, sorry, just a other picture for something that is happening somewhere else, yeah? Maybe I can use other names in order to avoid confusing you. L5 and L6, okay? Good. So somewhere we have EV1, the x coordinate, in A, and we have L5 and L6. And let's say the root vertex is somewhere here, yeah, R. So we cross over L5 to x1 and then not anymore. So V1 shows up here. Sorry, I also have to come up with new names for my direction vectors. So what should this direction be? U, okay? U is not used. U, the x-coordinate of U, is U1. Okay, U1 shows up here, here not. Now, if we look at EV for points behind wherever this is connected to R, for points behind R, let me say, then they also need U1, U2, but they also need U1, U2 here, right? Any point that is not x1, only x1 I stop here. For everyone behind that, I have to cross over both of them. Okay, what does that mean? That means I can yet again perform some operation in A now, just in this block A. You saw already that we decomposed, right? The big determinant that we care for is now the determinant of A times the determinant of this guy, right? We'll talk about this guy later. Now we're talking about the determinant of A. in the determinant of A, in this A, this thing is showing up, and we can go and erase this and this. Okay, and this will produce a factor of U1 times, well, something, and that something is going to be the determinant where we just forget about that point, right? We're just not evaluating that x coordinate anymore. And what is U1? U1 is the x coordinate of my vector u, right? So how does the image of this look like? In the image of this thing, we see that x1 is a point, and this is u, and this meets the line. Now I have to pay attention to x and y coordinate again. This is my line that x1 meets, right? And it has direction 0, 1. 0, 1. And now what is the Bézout intersection multiplicity of those two guys? It's the determinant of u with 0, 1. Absolute value, of course. Well, that is absolute value of u1. Yeah? Okay, so that means we sort of simplified our matrix A, and we identified this factor here. It's showing up after simplifying the matrix A, okay? And of course, we can perform precisely the same operation for this thing, because in A, there's also the line for x2. We just throw it out, producing that factor, and work with the remainder of the matrix. Now, what is the remainder of the matrix? The remainder of the matrix A, well, it's just an evaluation, right? It just evaluates those points behind E1, behind E2, where I have to be a little bit careful, where I'm sort of putting my R, I'm moving my R to be here, and I'm treating this edge as just one edge of this length, which I can do because it straightens, right? This is just a contracted edge. Yeah? But once I do this, this remainder of the red part that is still there is nothing but the evaluation at the mark points that I have in here. Yeah? So this A is this. Those, the three green parts together are the absolute value of the determinant of this A that I have. Yeah? Okay, we still have to investigate what the lower part is. So now we focus on this part. Now we focus on here. And what do we want to compare it with? Well, there are two factors which we have not yet understood. And one of them, which is a very important factor, is, of course, the evaluation multiplicity of my C2. I'm not so sure what to erase, I have to admit. Let me try to get away by erasing just a little bit here. The standing board, great idea, thank you. It is pretty though, but yeah. Yeah, sorry, Thomas. Okay. So let's consider the EV matrix for C2. How does it look like? C2 being that part over there. Again, we cut here. We forget that this path was here. We straighten. And we just assume that here's our root vertex. Let's call it R prime. And we sort of identify those two to be just one length as we go through here. So we have the H of R prime columns. We have this new length, but let me call it L3 plus L4. And we have whatever length in C2, right? So we have points behind E3, and we have points behind E4, right? To go to points behind E3, points behind E3, these are those, right? So from R prime, if I start from here, I don't need to use anybody here. Well, I do have my root vertex, of course. Then I don't need anything here. And then I have whatever I have, what I also had in this matrix here, of course. And to go to behind E4, now coming from here, I need to cross over my new length. So I have a minus W here. And then I have something. Okay, good. Now look at this matrix, and please notice that it differs from the matrix I care for only in the first two columns. This right part is already okay, yeah, because the stars were actually the same stars. Yeah? The stars were talking about how to reach the points here and how to reach the points here, and that is not changed if I cut here, right? Okay, so this is the same part. This is the same part. And now I can do the following. I can take this matrix and multiply on the right with a matrix that has VW and then only once. Yeah, so a 2 by 2 block containing V and W and only once. If I do this, I get from this, via multiplication with this, to precisely here. Okay, now this is this. And what's the determinant of this thing, which we artificially factored along here, right, to get here? That is just the determinant of this little 2 by 2 block. But what is this little 2 by 2 block? It's the vectors V and W. What is the image of this thing here? It's like a cross and an intersection. This whole guy is contracted, right? And this is V, and this is W, yeah? And what is the intersection multiplicity, the Bézout intersection multiplicity? Well, precisely that determinant, the determinant of V and W. So we also identified this thing, and those two blue factors together are exactly the determinant in this lower block here, okay? Good, so the lemma is proved, and that was the most we had to do, sort of. Okay. I want to keep this. I think I can get rid of the big matrix now. So we need one more observation. What have we done so far? We discussed curves in the pre-image of my special point configuration P1. P1, which is still up there. No. Anyway, it's my two lines, my points P3 up to Pn, and this very long guy separating 1, 2, and 3, 4. We analyzed pre-images in there. We found a bunch of them which have the contracted bounded edge like this, and which give us a contribution of ND, right? The remaining ones we now discussed contribute something that decomposes in such a way, okay? What I now need to convince you of is that I can sort of go reverse. If I have a curve of degree D1 through 3D1 minus 1 of my points, and if I have a curve of degree D2 through 3D2 minus 3 further points plus 3 and 4, yeah? Then I claim I can take those and produce a pre-image in there. How do I do that? Well, there are also my two lines around, L1 and L2. So first, let me consider C1. It meets L1 somewhere. Yeah, actually maybe in more than 1 point. Yeah, in actually counted with multiplicity D1 points, right? But I choose one. And this is where I say, okay, I want this to be h of x1. I just add a marking there. Yeah? Then I choose another intersection point with this other line. So of course also 2 of those. Yeah? I choose one and I declare this to be where my mark point x2 is. Then those two curves intersect in D1 times D2 points. I choose 1 and build in a contracted bounded edge in between. Yeah? The length of the contracted bounded edge I have to pick in such a way that the forgetful map precisely maps to my long guy. Yeah? So from this picture, consisting of 2 separate curves, I produce a unique guy in the pre-image. Yeah? And with that, I now have a bijection between remaining guys in the pre-image and decomposed curves. And now I can count. So here's the theory, the Kontsevich formula for tropical curves. It states that ND trop is equal to the sum of D1 plus D2 equal D, where both D1 and D2 are bigger 0. D1 squared, D2 squared. Yeah, let me erase this, not needed anymore. (3D minus 4), choose 3D minus 2, minus D1 cubed, D2, 3D minus 4, choose 3D1 minus 1, that all in brackets, and then ND1 trop, and D2 trop. Okay, what is the proof? Well, the proof starts as we started. We consider our map pi, we choose our P1 and our P2 as before. Okay. We already know that each point, because of our special choice of P1 and P2, each tropical stable map in the pre-image will have a contracted bounded edge. And we know that there are, on the left side of our equation, there are 2 sorts of contributions. So on the left-hand side, we have a contribution which is just ND. And then we write plus. Okay, and everybody else splits, as I promised here. Yeah? So everybody else is a curve, is 2 curves of degree D1 and D2. They have to sum up to D, of course. They both have to be bigger than 0, right? Then I have to choose. So I have originally I have 3D points, but there are the 4 special ones, and the 4 special ones are already distributed, 1 and 2 on C1, 3 and 4 on C2. But I need to choose 3D minus 1 of the remaining 3D minus 4 points that go on C1, right? So this is the choice of 3D minus 1 points among x5 up to xn that go to C1. Yeah, so I have my picture with these points. I choose from the 3D minus 4 those 3D minus 1, and I draw my tropical curve C1 through those, right? Then I have a choice of intersection point with L1. Okay, and this is where I put my mark x1. Yeah? Then I have a choice of intersection point with L2. And then I have a choice of intersection point between the 2 curves where I pick where the contracted bounded edge has to go. Choice of intersection of C1 and C2. And, well, then I count the curves ND1 and ND2. Yeah? For each choice of 2 curves in here, enhancing them in this way, I produce precisely 1 guy in the degree of pi. So this is the degree at P1 of pi. And that's one side of the equation. Yeah, I think I can get. Oh, yes, I can. Now what's happening on the other side? We have actually not at all discussed the other side, but I'm convinced that you are fully aware that this, of course, works precisely in the same way, with the exception that, of course, now no two marked points can sit together next to the contracted edge. We discussed this already, because that was a specialty of only 1 and 2, because they had to meet lines, and 2 lines meet in a point, that's fine. But any other marked points, they have to meet different guys, so they cannot live together. So on the other side of my equation, I will just not have a contribution analogous to this. I will have only those guys. Yeah? And with those guys, it's sort of the same, except that now the points are different. 1 and 3 are on C1. 2 and 4 are on C2. The rest goes through, okay? So what do we have on the right-hand side? We have the degree P2 of pi on the right-hand side, and it is just a big sum of d1 plus d2 equal d, d1, d2 bigger 0. We have those 3d minus 4 points, x5 up to xn, where we need to choose who goes where. Now we have to pay a little bit attention, because C1 already got 1 point which evaluates a point, namely 3. 1 we'll forget, it just maps to a line. But there's 1 point condition, number 3. So we need only 3d minus 2 further points to make the dimension count work out and to make our red blocks to be actually square, right? So 3d1 minus 2 is what is needed here. And this is the choice of points in addition to x3. Choice of points in addition to x3. Okay, then we have a factor of d1, and this is the intersection of c1 with L1. It's supposed to be a d1, sorry. Then we have a factor of, careful, d2 now, because 2, the mark point number 2, sits on c2, right? So now we're intersecting c2 with L2 and putting our mark number 2 somewhere there, right? Then we have a factor of d1, d2, which is the intersection of c1 and c2, and we just pick where to put our contracted bounded edge, right? And then we have all this times nd1 drop and d2 drop, because yet again, for every pair of curves contributing to here, I can play this game, adding my contracted bounded edge, adding x2, adding x1, after I have chosen which goes through which points, right? And then I have my one unique guy in the pre-image. Yeah, and now we look at this. We take all this, put it to the other side of the equation, and that's our recursion, right? Yeah, so that's it. That's the proof. That's the Kontsevich recursion, proved via tropical geometry using the theory of tropical moduli spaces of relative stable maps, of linear maps between marked fans and the fact that their degree is constant. And other than that, you know, it's just sort of a combinatorial game once you understood those pi multiplicities of those curves. Yeah, okay, so I hope that you like it. I like this formula, I have to say. I like the combinatorics. Good. So that's it. Time for questions. Thank you.